Welcome to week 3 of Classical Mechanics 2. This week we're going to be talking about quite a number of things. The first thing we're going to be talking about in this video is linear operators, and then we're going to go on and look at driven oscillators and Fourier series solutions to differential equations, although those last two are optional topics. Then we're going to be looking at coupled oscillators in the next video and how we model interacting systems in the video after that. These all will go together into a unit based around graphical solutions to differential equations. So some of these problems we can solve analytically, but some of them we can't. And so then we'll have to turn to graphical solutions in order to study the dynamics of these problems. The driven oscillator is basically the regular oscillator that we talked about last week. This is just a regular damped oscillator, and then we're going to imagine that there's a force acting on the mass that's going to depend on time. X double dot plus 2 beta x dot plus omega naught squared x is equal to the driving force divided by the mass. So this is the generic type of problem we're interested in solving. But before we get there, I want to do a brief aside into linear operators. So when I talk about an operator, this is in our case the differential operator for the driven oscillator. What I'm basically done is I've pulled out all of the derivatives and all of the constants from this. And so now I'm taking this d as a function and I'm acting it on my variable x. So what I would write now is d of x is equal to f of t. And so linear operators have some really nice properties, and these are properties that we use time and again in solving different types of physics problems. So one of the properties is that d acting on a constant times our function x is equal to a times d of x. The other property is d acting on two functions x plus y is equal to d acting on x plus d acting on y. And these two properties together define an operator as being linear. But when we combine them together, we end up with a property called superposition. And this is something that is used at all different levels of physics. For this, imagine that I have two solutions, x1 and x2, that both solve d of x is equal to 0. That means that I can come up with an even more general solution, which is d acting on some constant times x1 plus some constant times x2 is equal to 0. So that means that solutions to any equation that comes from a linear operator can be these superposition solutions. So these are weighted sums of all possible solutions. The other thing we have to think about are inhomogeneous equations. So homogeneous equations are my differential operator is equal to 0. But here it's not equal to 0, it's equal to f of t. And having it equal to a function makes this an inhomogeneous equation. Imagine that I've come up with some particular solution, xp of t, that solve this differential equation. So I've got dx is equal to f of t, and imagine that I have xh, the homogeneous solution to dx is equal to 0. So imagine that I have these two solutions. Doesn't matter now where I found them, but just imagine they exist. And I can come up with the most general possible solution to my original equation, so dx is equal to f of t. And that solution is going to be the x particular plus constants times my homogeneous solutions. And so these are linear superpositions of solutions. But it's important to note that I can't put a constant outside my particular solution. So if I were to do that, imagine I had A times xp of t. That means that this is going to be equal to A times d acting on xp. And if I go over to my function here, that means I have A times f of t. And that's not the equation that I was trying to solve. That is a multiple of the equation I'm trying to solve. So that's why we can't have a constant acting on xp. So let's imagine for a second that I have a special type of driving motion. I've got sinusoidal driving. So that tells me that my force is going to be a cosine of omega dt. So omega d is my driving force. What I'm going to do to solve this is basically a trick. It's similar to things we've talked about in last week's videos, where we go from a sinusoidal solution to something that is a complex exponential. So we're going to do exactly that. We're going to change variables. So I have, instead of x, I'm going to have z, which is x plus iy. This is a nice thing to do because we can take advantage of the geometry of the complex plane to help us with our solutions later. So this is the complex plane. I've got my point z here. So the real part of this, of z, is going to be x, and the imaginary part's going to be y. But I can equally well write this in terms of an amplitude. So A is the magnitude of z, and delta is its phase. So now if I want to write down a solution for my differential equation, I can write down a function in terms of z. So this is going to be z double dot plus 2 beta z dot plus omega naught squared z is equal to f naught e to the I omega dt. Since our driving force goes like e to the I omega dt, it makes sense that we pick a solution that goes like e to the I omega dt. So let's guess our solution. C is equal to e to the I omega dt. When we plug that into our equation here, we end up with C times minus omega d squared plus 2I beta omega d plus omega naught squared. All of that times e to the I omega dt is equal to f naught e to the I omega dt. And so we've got these two time components here, and they cancel out. So now we could rewrite c, this constant that's modifying our z term, in terms of the constants in our problem. So beta, omega d, omega naught, and f naught. If we want to get the actual solution, x is the solution we're looking for, so we're taking the real part of z, we want to be able to split this whole thing into its complex components. So if I write down c like this, it looks a little bit nasty as far as this is concerned. I've got 2I beta omega d in the denominator here. And so what I'm going to do is I'm going to appeal to my form of complex numbers, which is an amplitude times a phase, in order to sort out the real and imaginary parts of C. So at the end of the day, I want to write C as A e to the I delta. So for the amplitude portion of it, I'm going to take C and multiply it by its complex conjugate. So this basically means I take the real part as the same, but I switch the signs of the imaginary part. So this tells me that I have e to the I delta times e to the minus I delta times a squared. I can plug this into my definition for C here, and I end up with an equation for a squared. So this is equal to f naught squared divided by omega naught squared minus omega d squared, quantity squared, plus 4 beta squared omega d squared. So for the phase, I want to look for what this angle is here. And so what I'm going to do is look for, look at this in terms of a right triangle. So I've got a real side here and the imaginary side here. So the angle delta is the arctan of the ratio of the imaginary piece to the real piece. I'm going to extract this information from C by, in a clever way, multiplying this by 1. So I have A divided by F naught is equal to omega naught squared minus omega d squared minus 2I beta omega d. From this, I want to extract the real piece and the imaginary piece. And so delta is going to be equal to the arctan of the imaginary piece divided by the real piece. And we end up with arctan of 2 beta omega d divided by omega naught minus omega d squared. And I can combine this all together into one equation for z. So now I have z is equal to c e to the I omega dt, or this is equal to a e to the I times omega dt plus delta. And then I just take the real part of this, so a times cosine omega dt plus delta, and that is going to give me my final solution. This is the particular solution to this problem. And then, as we said before, I add to this a superposition of the homogeneous solution and fit that to the initial conditions. So let's have a look at what the consequences of this are. And this is going to go under the title of resonance, and we'll see why in a minute. Imagine I have this superposition of solutions. So I've got my homogeneous component and my particular component here. So I have something that has some exponential decay, and maybe it has some oscillations in here too if part of R is imaginary. But there is always going to be some exponential decay in my homogeneous solutions. And to that, I'm going to add my A cosine omega dt minus delta. We know that these terms, these decaying terms, are going to go to 0 as time goes to infinity. So for long times, the only term in our system is going to be dependent on this term related to driving. So let's plot the amplitude and see what happens at long times. This is a plot of the amplitude squared as a function of omega d. This is assuming that omega naught is something that's fixed, and we're just going to scan through possible driving frequencies. So for low frequencies, we get some sort of constant, or like a small amplitude. And as we increase, this is going to increase up to some maximum omega star. So this is a very large amplitude response. And then from there, it's going to decay away. So this omega star, here we're looking at the maximum of A. So we're looking for a place where dA by d omega d is equal to 0. And we find that that peak solution, the resonant frequency at omega star is equal to the square root of omega naught squared minus 2 beta squared. This is going to be the frequency that maximizes the amplitude. So as you're scanning through the frequencies, at some point you're going to have a very large response of your driven system, and it's going to happen when you drive it at exactly this omega star. So we've introduced a whole bunch of notation here. So let me match the notation up with terminology. So omega naught is our old friend, the square root of k over m. This is the natural frequency of the mass and spring system. Omega d is the driving frequency. Omega tilde is the underdamped frequency. So if we have a system with weak damping, it's going to oscillate, but it's not going to oscillate at the natural frequency. It's going to oscillate at a slightly lower frequency to that. And then we also have this resonant frequency, omega star. So this is the frequency that if you were to drive your oscillator at, this is the frequency that gets a very large response. The last thing we're going to talk about in this lecture is Fourier series solutions. This is basically answering the question, what if f of t isn't sinusoidal? Imagine it's this square wave. So it's something periodic, but not something sinusoidal. So it has some width of signal, and then it has some amount of time, we're going to call it tau, in between frequency cycles. So what we're going to do is we're going to Fourier expand f of t. So in order to Fourier expand this, this is going to be the sum from n equals 0 to infinity of some constant times cosine n omega t plus some other constant times sine omega nt. And these constants are given by these definitions. A0, so this is the constant term when cosine of 0 is equal to 1, the term is going to be 1 over tau times the integral from minus tau over 2 to tau over 2 of f of t dt. And then the two subsequent constants, so an for n is 1 or greater, and bn for n is 1 or greater, are going to be 2 divided by tau, and then the integrals are both from minus tau over 2 to tau over 2. F of t are going to be times cosine n omega t dt, and the bn's are going to be times sine n omega t dt. These are going to give you the definition for the constants that go in here, and then basically the larger the number of terms you keep here, the closer to the solution you're going to be. Our particular solution is going to be a sum of all possible xn. So basically there's like an x0 term that's going to be related to the constant term here. And then there's, an x1 term that'll have a cosine piece and a sine piece, and so on and so forth. Xn of t is equal to an cosine n omega dt minus delta n. And the definitions for an and delta n are quite similar to the formulas that we worked out for the amplitude and phase shift of the driven oscillator. However, all of the terms that used to be omega d are now n times omega d. So we've got n squared omega d squared in the denominator here, and we've got n squared omega d squared here. So we can use this type of Fourier series expansion in order to solve for any type of wave you might have. And in a later video this week, I will have a brief explanation of how you can use Mathematica to solve these for you.